I welcome everyone to this video. I am Mr. Rish. Thank you for joining me. I am looking here at the hydrazone mechanism and we will examine how the hydrazone compound forms. What are we talking about? We saw something similar to this in the video prior. If you want to get rid of a carbonyl and convert it into an alkane, you will use hydrazine. You know this from the previous video. Hydrazine, NH2, NH2. You will develop a hydrazone compound which will look something like this. The oxygen has been lost in two hydrogens and a water will be given off. This oxygen and these two hydrogens will come off as a water. You've added your hydrazine onto your compound. This right here is a hydrazone ketone. How does this form? And what's the purpose of doing all of this? Because you will reduce this now and you will generate your CH2 and your diatomic nitrogen is lost. But you've converted a carbonyl into an alkane by means of using a hydrazine to develop a hydrazone. Now we will look at the mechanism of formation of this because you need to know this. How does the hydrazone compound form? And it's a hydrazone ketone because you'll still have an R group here, and it'll be a ketone, except rather than the carbonyl oxygen, you'll have a carbonyl hydrazine added to it, so it's called a hydrazone ketone. And let's look at the mechanism now. Now let's see the mechanism of this hydrazone formation, the hydrazine adding to your ketone, and it's an interesting mechanism. I have dimethyl ketone or acetone. I'm drawing my hydrazine right over here. It's NH2 and NH2, and you keep in mind all the electrons are involved. This NH2 component will not be involved at all. The entire reaction will involve this NH2 with everything else. And keep in mind, this oxygen, these two hydrogens will be lost to give off a water. This will add to your double bonded carbon. Now how will this occur? You have a Lewis-based oxygen, Lewis-based nitrogen, so you're not going to add on the oxygen, you'll add right here to the carbonyl carbon because it's charge deficient, or you can say it's an electrophilic site. Because when you're looking at a carbonyl, you have here a partial negative, partial positive. The dipole is in the direction of the oxygen. Hence, that's the perfect site for adding. The carbonyl carbon is electrophilic site. When it adds, these two electrons will be lost of nitrogen to form the nitrogen carbon single bond, and this is what I'm talking about. I have CH3, I have my CH3, and the two electrons of this single bond right here will go into oxygen, and you will see the shuffling of electrons like this. Keep in mind, oxygen normally has 4 electrons or 2 pairs. Now we have 3 pairs, but 6 electrons is charge excess. It's relatively dense, negatively charged. The 2 electrons here have been generated in the nitrogen bond. You still have the hydrogen, you still have the hydrogen, and you have this NH2 which won't be utilized in any way at all. I will have here a charge deficiency on the nitrogen because it has used its 2 electrons in the formation of a bond. It doesn't have complete ownership of that electron, so it's charge deficient. Now what will happen? I'm just going to transfer the NH2 here, my hydrazine. I'll remove it from here because you see this NH2 will never be involved. The reaction will always involve this NH2. The site of reaction, the addition, was my electrophilic carbon. And now what we will have is the proton transfer. How will that proton transfer occur? Look at this oxygen right here. It looks something like this. This is what it is. And look at one of these hydrogens attached to a nitrogen. It looks like this. And then you have everything else added. You will have here a proton transfer. These 2 electrons will be involved here to snatch the hydrogen. The 2 electrons of this bond will be returned back to nitrogen. In essence, what I'm saying is these 2 electrons will pull the hydrogen back. The 2 electrons will be returned to the nitrogen. The proton will transfer from the nitrogen of your hydrazine to your oxygen of your carbonyl, and that right there is your proton transfer step. I will have CH3, CH3. I have right here my nitrogen. The 2 electrons of this nitrogen hydrogen band have been returned to the nitrogen, so it looks like this. And then I have my NH2, this NH2 which is not being utilized at all. Now I am looking here at the oxygen. It has lost its charge deficiency because these 2 electrons of the oxygen which are excess or extra will be utilized in the oxygen hydrogen bond. You see them right here. You have the other 2 pairs like that. Now we have this. I started here my addition of my hydrazine to the carbonyl. Then I have my proton transfer from the nitrogen to the oxygen, and that's where I am. What happens now? I will use these 2 electrons over here to generate a double bond, and this entire hydroxyl functionality will drift away. It will drift away. And you are looking at this. Look, here's my CH3, my CCH3. My hydroxide will drift away, and I'm going to write my hydroxide as this OH and with a minus. Why is it a minus? Because it's got an extra pair of electrons. The electrons, the two electrons of this carbon-oxygen bond will be retained by the hydroxide, hence it's nucleophilic. It's become a nucleophile. It has an excess of charge. These two electrons of this bond are retained by hydroxide. These two electrons of the nitrogen will go here to form a double bond, and you're looking at it. A hydrazone compound is beginning to form. The hydrogen is still over here, and I still have this other NH2 which is not involved in any way. Now I'm back to a positive charged nitrogen. Is charge deficient because it has utilized its electrons, both of them electrons, to form another bond with carbon, and it is not having full retain or ownership of those electrons, so it's charge deficient. Now the last thing which happens is you're going to lose the hydrogen on this nitrogen to make this a water. And how would that happen? You have this hydroxide group right here. It's going to snatch this hydrogen. These two electrons will go back to nitrogen, and you will end here at your end result, CH3, C, CH3. I have my double bond nitrogen, and then I have my NH2, which has not been utilized in any way. And you have retained these two electrons of this bond to your nitrogen. It looks like this. The OH minus has snatched that hydrogen. It has used two of its electrons to form a bond with the hydrogen, so you'll have your water, and it looks like this. And your water is given off. That's right there, your byproduct. OH minus used two of its electrons to pull that hydrogen and generate a bond. And you're seeing this bond right over here. My first step is the addition of hydrazine to my electrophilic carbon. That's my addition step. Then I have a proton transfer from the nitrogen to the oxygen. Then I have a departing, an elimination of hydroxide. The hydroxide groups, the OH groups, hydroxyl departs. It's a elimination step. And then finally I have over here a deprotonation step, where this proton is deprotonated by the hydroxide to generate water, and I've developed here my hydrazone. My hydrazone here is going to be dimethyl, and we'll say ketone hydrazone, dimethyl ketone hydrazone, or you know what you can call it? You can also call it acetone hydrazone. Dimethyl ketone hydrazone or acetone hydrazone, either of those names is good. I'm just erasing this so it doesn't look too messy. There's one more thing I should show you before we go. This oxygen right here was lost right over here in the leaving of this OH. You see the oxygen right here, it's lost. You have one hydrogen here which was pulled off your hydrazine compound. You see it right here. It became part of your hydroxyl and was lost with the OH. You have the OH lost, so you've lost one oxygen, one hydrogen from your hydrazine, your oxygen from your carbonyl. Your other hydrogen is lost right here from the other hydroxide, which plucks it off in the deprotonation step to generate water. So you in essence lose these two hydrogens from your hydrazine, and you lose this oxygen from your carbonyl. You have this water right over here, and the hydrazine adds to your compound to develop your hydrazone. So that right there is the end of the reaction mechanism, and it's good. Addition of hydrazine to your carbonyl, proton transfer, elimination of the hydroxyl functionality to generate a hydroxide anion, and finally deprotonation step of your hydroxide, involving your hydroxide to generate water, and your hydrazone compound, dimethyl ketone hydrazone or acetone hydrazone, and the reaction mechanism is good. This compound now is primed for a reduction reaction, and you know Wolff-Kishner reduction reaction, I've shown that in a previous video. This can now be converted into an alkane. The CH2 will come out from right here. You'll reduce a carbonyl to a CH2 by means of the hydrazine addition and reduction of your hydrazone. That right there is the end of this video. Thank you.